already kind of finished the shear force and bending moment diagram, right? So this was last time. These were our equations, and from here we kind of drew the shear force and bending moment diagram. So now today, what we can do is that we can like do another example, and we can try to draw a shear force and bending moment diagram for this case. So this is a kind of complicated, uh, uh, simply supported beam because you have a like linearly increasing distributed load, and also you have a point load. So we'll try to use the same method, which is like cutting a section and just like uh, drawing the like calculating the internal loads, and then from there we can draw the shear force and bending moment diagram. So we're going to use the same method, and then in the next lecture probably we'll discover another method which is called graphical method. So there are two broad methods to draw shear force and bending moment diagrams. So this is the one which is called equation method, which we are doing it right now. And then in the next time, we'll just explore a little bit of graphical method. So we'll do this example, and we'll follow the same procedure which we were following before, and we'll see how the shear force and bending moment diagrams are in this case. So this is, I guess, last example of this chapter 5 of the workbook. So this is a simply supported beam, right? This one. So this is a simply supported beam. It has length 8 meter. So what we have to do is, the first part is we have to draw free body diagram. So let's draw free body diagram for this case. So we have a simply supported beam, and we have two loads. One is a distributed load with a trapezoidal shape, and the minimum value is 3 kilonewton per meter, and the maximum value is 5 kilonewton per meter. And then we also have a point load of 8 kilonewton, and the total distance is 8 meter. And for the trapezoidal load we have 4 meter, and for this we have 2 meter and 2 meter. So it's a simply supported beam, so we'll have two reactions at the pin support and one reaction at the roller support. So if I want to call this point A and this point as B, so this force would be AY, this force would be AX, and this force would be BY. So I want you guys to calculate the reaction forces, and you guys can let me know what would be the reaction forces. So I can convert these loads, these distributed loads into a point loads. I can also represent this figure. So we have AY, we have AX, we have BY, and we have a load of 8 kilonewton. This distance is 2 meter, this distance is 2 meter. Now we can also convert this triangular trapezoidal load into point loads. So we can first convert these into a triangle and a rectangle. So this is a triangle, this is rectangle. So this distance would be, I can draw a little bit bigger here for you guys to see. So this distance is 3 kilonewton per meter, and this distance is 2 kilonewton per meter, right? So if we calculate area for this part, which is, this is 4 meter. So it's going to be 3 by 4. This is 12 kilonewton, the area for this triangle. the area for this triangle would be 1 by 2 into length into height. So it's going to be 4 kilonewton. So there is one force which is acting. This is a rectangular force. This is 12 kilonewton. And then there is another force which is going to be acting here, which is 4 kilonewton. And we can also calculate the distances. This distance is going to be, this total distance is 4 meters. So this distance is 2 meter. And this distance is 2.67 meter. Because when we'll do summation of moments, then we also need to know where these forces are acting. So now let's try to calculate the reaction. If you do summation of f of x is equal to 0, you're going to get a of x is equal to 0. So I'm going to do, this is a point, this is b point. I'm going to do summation of moment at a is equal to 0. So in this way I will get 12 kilonewton force. This is clockwise, so negative into 2, clockwise minus 4 into 2.67, clockwise minus 8 into 4, 6, and then anti-clockwise positive by into 8 is equal to 0. So if you solve for this, you're going to get by is equal to 10.33, sorry, you're going to get force 10.335 kilonewton. So I have taken moment along this point is equal to 0. And if you do summation of f of y is equal to 0, it's going to be ay plus by minus 12 minus 4 minus 8 is equal to 0. And you're going to get the value of ay as 13.665 kilonewton. And the ax is 0. So let's try to, so now we're going to do shear force and bending moment diagrams, right? And for that we have to make a cut. So let's talk about all the cuts here. I'm going to draw cut 1 here, I'm going to draw cut 2 here, and I'm going to draw cut 3 here. So this is how it looks like. And this is our cut. This we know is 3 kilonewton per meter. And our load, this we already know, this is 13.665. And this is the distance x. And then for the cut 2, I'm gonna use the first part. We can also use the second part. The second part is gonna be easier, but for this example, we can use the first section of the cut. This is going to be the cut, and this is going to be the distance x, and this is going to be the force. And we know the value. This is 3 kilonewton per meter. This value is 5 kilonewton per meter. And then we're gonna draw third cut. Third cut also, we can either select the first part of the cut or we can select the second part of the cut. So in this case, I'm gonna select the remaining part because it looks easy. This is the force, this is the cut. So these are the internal loads. This is shear force, this is bending moment, this is shear force, this is bending moment, and this is shear force and bending moment. And this distance would be this entire distance is 8. If we assume this as x, this is gonna be 8 minus x. So yeah, so in this case, so I made a cut here, right? So from the figure, it makes sense to us. Like we have made the right cuts, right? One here, one here, one here. So we have made the right cuts. So if we're gonna make a cut, we can either select this part or we can select this part. So I've selected this part for the first cut. And when I made a cut, we can select this part or we can select this part. So I selected this part, but it would be easier to select this part, right? But if we make a cut 3, then either we can select the whole this part to do the calculation or this part. So I've decided to select this part. So in this way, I mean, we weren't able to get this 8 kilonewton force. But if you will select the first part, then you will get the 8 kilonewton force. So you can select either way. So for me, it seems easier if we will do the calculation from the second part. And then we have a load, and this load was 13.665. This is By, right? So By was 10.335 kilonewton. So now we have to formulate the equations. Now we have the cuts. Now we're gonna develop the equations for V and M for all the cuts. But I'm gonna also write this load is applicable from 0 to 4, these equations. This equation is gonna be applicable from 4 to 6, I guess. 4 to 6. This is going to be applicable from 6 to 8. Yeah, so these are the, like, we'll formulate the equations, and these equations are only applicable from this distance to this distance. And for this equation, V and M, the values will be applicable from 4 to 6, and from 6 to 8. These are the ones which are applicable. So now we can do the summation of forces along x-axis, y-axis, and we can try to calculate. So the first cut would be tricky because we don't know this point. So we cannot do summation of vertical forces because we need this point to calculate the summation of forces, right? So let's try to figure out how we can calculate this part. So we need this point, and somehow if we can get this point, the value of this point, then we can calculate the vertical forces. So we can do one thing. We know this distance, right? This distance is 3 kilonewtons. So we know this distance. All we need to do is calculate this distance. So I'm going to draw this here. So I'm going to draw a complete trapezoidal loading condition which we have. So that's the complete. I'm just drawing the loads, the load we had, and we'll figure out the distances. This point we know, and we made a cut somewhere here, right? So this we know is x. This point we know is 3. I'm not writing units for now. This distance we know is 5 total, right? This distance we know is 3. This distance we know is 3. This distance we know is 2. So we can calculate this point we know. This point, this is 3. We have to calculate this distance. So we know the slopes. The slope is same for both the triangles. This is also a triangle. This is also a triangle. So the slopes are same, and so I can write this way. So this is the height, which is 2, and this distance, this total distance is 4, right? So 2 divided by 4, which is slope, y divided by x. This is y. This is, I mean, if this is y, if this is x, let's call it capital Y, capital X. So if this is capital Y and this is capital X, so this is y divided by x, which is the slope. This is slope equation. Slopes is same for both the triangles. So this distance, let's call this distance small y, right? It would be equal to small y divided by small x. Does it make sense? So we can get the value, this y value would be x by 2. This is small y. This is x by 2. So I'm gonna write what we have now. We have shear force and bending moment. So this distance is actually x by 2, and this distance we already know, which is 3. So this distance we already know, which is 3 kilonewton. So now we have the distances. Now we can try to calculate the forces. So I am going to simplify this part. I'm going to draw it here again. So this was 13.665. This was a cut. We had a shear force, we have a bending moment. This is shear force, this is bending moment. Now we're going to convert these loads into point load, this trapezoidal load. So all we have to do is we have to calculate the area. So if we calculate the area of a triangle, if this rectangle, so the area of this rectangle is the area is length into height, 3 into x. So that's the load for a rectangle. Does it make sense? And then you will have another load, which is area of a triangle, which is 1 by 2 into x into the height, which is x by 2. So that's gonna be x square. That's gonna be x square by 4. I'm gonna write it here. So these are our loads, 3x and x squared by 4. Does it make sense? This is x squared by 4. We also need to know the distances, right, from here to here. So the distance for this force would be, if this is x, the distance is x by 2. And this distance is x by 3. So let me know if there is some confusion or if you think there should be something else. So all I have done is, like, I have broken down these two. So first step was to calculate these points, right? So I used a slope relationship to calculate these distances. So once we have the distances, this force is basically area of a rectangle, which is 3 into x, 3x. And then the triangle is half into length into height. So I got x squared by 4. And the force acts, this force is acting at 2 by 3rd of the distance x and 1 by 3rd of x. So this is x by 3 and this is the distance x by 2. Okay, so I'm gonna do, let's solve for this and try to calculate the value of V and M. Let me do one thing. Right, so if we do summation of f of y is equal to 0, also put this a bit down. All right. So let's do summation of f of y is equal to 0. From cut 1, you're going to get 13.665 minus this force, which is 3x, minus this force, which is minus x squared by 4, and then minus v is equal to 0. So in this way, you'll get the value of v as this. And if we do summation of moments, let's do summation of moment at a is equal to 0. Or I'm gonna, let's do summation of moment at a is equal to 0. So if you do summation of moment at a is equal to 0, you're gonna get clockwise minus 3x into x by 2. And another force is the next force is x squared by 4, and the distance is 2 by 3x. And then there's another force, which is shear force, which is clockwise negative Vx. And then we have a moment is equal to 0. This is what I'm getting. So if you solve for this, your moment will come out to be, we can also replace the value, wait. It would be easier if we do summation of moment at this point is equal to 0, because then we don't have to input the value of shear force. So what I'm gonna do is I'm gonna take a moment at this point is equal to 0. So maybe you can also do the same way, because otherwise you have to input, you can do it this way as well, but then you have to put the value of shear force, which is already an equation. So it's gonna be hard. It's gonna be a difficult task to do. So let's take a moment along this point is equal to 0. Then you'll cancel out the shear force, so it's gonna be easy. Yeah. So if I do summation of moment, so what we're gonna get is clockwise negative 13.665x, and then anti-clockwise positive 3x into x by 2, and then anti-clockwise positive x squared by 4 into x by 3, and then we'll have moment is equal to 0. So now this is what I'm getting, and from here you can easily calculate the value of moment. So the moment would be 13.665 minus 3x squared by 2 minus x cubed by 12. So this is equation 1, this is equation 2. So if you guys are getting the same, then it's okay. If not, then okay. So now we have equations for the cut 1 and cut 2. I'm gonna clean it up. I'm gonna write it down in the easiest way possible so that we can have a room for other as well. So my shear force is 13.667 minus 3x minus x squared by 4. My bending moment is 13.66x minus 3x squared by 2 minus x cubed by 12. And you can also see there's a relationship. If you integrate this thing, you're going to get this value. And if you're going to do the differentiation of this, you're going to get this value. So basically, moment is an integration of shear force. We can try to solve for this also. And I'm just going to write the final answer, but this is easy. These two are a bit easy to do, but I'm going to just write the answer for the cut 2. But I guess cut 2 is straightforward. So if we do the cut 2, you're going to get the value of shear force is minus 2.335. And the value of moment you will get is minus 2.335x plus 34.68. And if we do for the cut 3 is also pretty straightforward. Maybe you guys can do for the cut 3. So if we do the cut 3, we're going to get the value of V is equal to 10.335, and the moment value we'll get is 82.68 minus 10.335x. So this is equation 1, this is equation 2, this is equation 3, this is equation 4, this one is equation 5, and this one is equation 6. Because in this case, the loading is straightforward. You can convert it to rectangle and triangle, and then you can solve for this. So this is gonna be easy. The one thing is important to note is that I put 8 minus x here. So I'm assuming the distance is from the start. So to stay consistent, I've like kept the x same from the A point. So that's why it's 8 minus x. So uh, so now we have the equations we can draw, but we can do something else to figure out, like, so there are some relationships between the loadings and the shear force and the bending moment. So we're going to explore those relationships. So let's try to do the integration. So I'm going to talk about cut 1 for now. So let's try to do the integration of V. So if you do the integration, what you're going to get? I'm going to integrate with respect to dx. So I'm going to do the integration of V with respect to dx. So the V is 13.667 minus 3x minus x squared by 4 dx. So if you do the integration, you're going to get 13.667x minus 3x squared by 2 minus x cubed by 3. So this is basically the same equation. So if you do the integration of shear force, you're going to get bending moment. And we can use these tricks to like directly draw the shear force and bending moment diagrams from the question, but we'll explore that in a bit. And let's do differentiation. So I'm going to do integration of shear force. I'm going to also do differentiation of V. So if you do differentiation of V, V is d by dx of V. V is 13.667 minus 3x minus x squared by 4. So if you do the differentiation, this is going to go 0, right? And 3 is going to go out, x is going to become 1. And this is going to be 2x, 2 minus 1 divided by 4. So if you calculate, you're going to get minus 3 minus 2x by 4. And this is basically the value for the, this is actually loading. So if you want to calculate the loads, this is actually equation of the load. So you can calculate load at any point. For example, if you're going to put value of 4 here at x, you're going to get the value of load. So you're going to get this 5 kilonewton per meter if you're going to put the value of x here. So the reason I'm just doing this is to show you the relationship. So if you have a load, if you do the integration of the load, you're going to get shear force. If you're going to do integration of shear force, you're going to get moment. And similarly, if you're going to do the differentiation of moment, you're going to get shear force. And if you're going to do the derivation of shear force, you're going to get the load. This is just for your like understanding, like there are relationships between the shear force and the bending moment and the load. So I'm gonna So let's try to draw the shear force and bending moment diagrams from here. So I'm gonna, this is for shear force and this is for bending moment. This is shear force, this is bending moment. And we have total 8, right? 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So if we put 1 in this, so we're going to use from 0 to 4. From 0 to 4, we're going to use cut 1. From 4 to 6, we're going to use cut 2 equations. And from 6 to 8, we're going to use cut 3 equations. This is 0, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So you guys can like start using your calculator, put the value 0 at x and see what's the value of shear, plot it here, put the value of 0 at here, see what's the value of moment, put it here, this is moment, and give me the shear force and bending moment diagram.